Imagine standing outside on a clear night, looking up at the sky, and realizing that everything you see is moving away from everything else. Not drifting slowly, not exploding outward from a single point in space, but expanding in a way that stretches the very fabric of the universe itself. This idea, which now sits at the foundation of modern cosmology, was once shocking and controversial. At the heart of it lies a simple but profound relationship known as Hubble's law, a discovery that forever changed how we understand the universe, its past, and its future. Before we dive into how the universe is expanding, make sure you're subscribed to the channel. At the beginning of the 20th century, astronomers believed the universe was static and eternal. The Milky Way was thought to be the entire universe, and the faint fuzzy objects seen through telescopes were assumed to be clouds of gas within our galaxy. This view began to crack as telescopes improved and observations became more precise. Astronomers started to realize that these fuzzy objects, called nebulae at the time, might actually be separate galaxies far beyond the Milky Way. Still, even as the size of the universe grew in human understanding, the assumption remained that it was not changing in any fundamental way. This assumption did not come from observation alone, but also from theory. When Albert Einstein developed his general theory of relativity in 1915, he discovered that gravity would cause the universe to either collapse inward or expand outward. Because the idea of a changing universe seemed unreasonable to most scientists of the time, Einstein introduced a mathematical term known as the cosmological constant to hold the universe in a stable, static state. It was a theoretical adjustment made to preserve a belief, not to explain an observation. Unknown to Einstein, the universe itself was about to prove him wrong. The key to this revelation came from studying light. When astronomers analyze the light from stars and galaxies, they can split it into a spectrum, much like a rainbow. Within the spectrum are dark lines that correspond to specific chemical elements. These lines act like fingerprints, telling astronomers what an object is made of. But they also reveal something else. If an object is moving toward us, these spectral lines shift slightly toward the blue end of the spectrum. If the object is moving away, they shift toward the red end. This effect, known as redshift, became one of the most powerful tools in astronomy. In the 1910 and 1920, astronomers such as Slipher began measuring the spectra of distant galaxies. Slipher noticed something strange and unexpected. Most galaxies showed redshifted light, meaning they were moving away from us. Even more surprising, many of them were moving away at tremendous speeds. At the time, these results were puzzling and lacked a clear explanation. The missing piece was distance. Astronomers knew these galaxies were moving away, but they did not yet know how far away they were. This is where Edwin Hubble enters the story. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble studied a special type of star called Cepheid variables. These stars brighten and dim in a regular pattern, and the period of their variation is directly related to their true brightness. By comparing how bright a Cepheid appears to how bright it actually is, astronomers can calculate its distance. Hubble used Cepheid variables to measure distances to nearby galaxies, conclusively proving that they lay far outside the Milky Way. The universe was suddenly far larger than anyone had imagined. Hubble then combined his distance measurements with redshift data collected by Slipher and others. When he plotted galaxy distance against recession speed, he found a remarkable pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship was strikingly simple and consistent. In 1929, Hubble published his results, revealing what we now call Hubble's law. In simple terms, Hubble's law states that the velocity at which a galaxy recedes from us is directly proportional to its distance from us. This discovery carried a profound implication. It was not that we were at the center of the universe and everything was moving away from us. Instead, space itself was expanding. To understand this, as the universe expands, galaxies move apart because the space between them is stretching. Every observer, no matter where they are located, would see other galaxies moving away. Hubble's law does not describe galaxies flying through space like shrapnel from an explosion. Rather, it describes the expansion of space itself. This distinction is crucial. Galaxies are mostly stationary within their local regions, held together by gravity. But on large scales, the fabric of the universe is stretching. This expansion affects only vast cosmic distances. It has no noticeable effect on smaller structures like galaxies, solar systems, or atoms. The constant of proportionality in Hubble's law is known as the Hubble constant. It tells us how fast the universe is expanding at the present time. If the Hubble constant is larger, the universe is expanding more rapidly. If it is smaller, the expansion is slower. Measuring the exact value of the Hubble constant has been one of the central challenges in cosmology, and it remains an active area of research today. Different methods of measurement currently give slightly different results, a problem known as the Hubble tension, which may point to new physics beyond our current understanding. One of the most important consequences of Hubble's law is that it implies the universe had a beginning. If galaxies are moving away from each other today, then in the past they must have been closer together. Rewinding the expansion backward in time leads to a state where the universe was extremely hot, dense, and compact. This idea became the foundation of the Big Bang theory. The Big Bang was not an explosion in space, but an expansion of space itself from an initial hot and dense state. Together, these observations confirm that Hubble's discovery was not an anomaly, but a fundamental feature of reality. Beyond its scientific significance, Hubble's law has a deeper philosophical impact. It tells us that the universe is dynamic, evolving, and finite in age. It reminds us that change is built into the fabric of existence itself. Since the universe is not as land, it is expanding, evolving, and filled with mysteries yet to be understood. As we look deeper into space and further back in time, Hubble's law remains one of the guiding principles of cosmology. It connects observation with theory, data with meaning, and the present universe with its distant past. What began as a simple plot of points on a graph became a doorway to understanding the origin, structure, and fate of the universe. And as our instruments grow more powerful and our theories more refined, the legacy of Hubble's discovery continues to shape our quest to understand the cosmos.